Alright, Logic fans, welcome to our second video on 6.8, Theorems 1 and Central Syntactic Concepts. And now that you've got down the idea of what a theorem is, how to go about proving it with reverse engineering and different techniques that you need to use, I want to introduce a couple of important and central syntactic concepts. So the first one I want to introduce is the concept of being syntactically logically equivalent. So let's just start by thinking about an example for a second. So consider these two sentences. Okay, everything is such that either it's F or it's G, and everything is such that either it's G or it's F. Now, intuitively, these are logically equivalent sentences, right? This is going to be true if and only if this is going to be true, and vice versa, right? So intuitively, they're logically equivalent, and you can kind of see that, if you use com, you can get the one from the other. All right. If you hearken back to chapter 5, when we were doing quantificational semantics, okay, we saw that a pair of quantificational sentences are semantically logically equivalent if and only if they take the same truth value on every possible interpretation. Now, we could not prove two sentences like these two to be semantically logically equivalent, not using those semantic techniques expounded in chapter 5, because there are just too many possible interpretations. You'd have to show something on every single possible interpretation, namely that whenever this one was true, and vice versa. Okay, and there was just we just didn't have the resources, the techniques to be able to prove something like that at that point. Fortunately, now we can say that a pair of quantificational sentences alpha and beta are syntactically logically equivalent if and only if it's a theorem that the first sentence tribar the second sentence. Okay, so by showing it's a theorem that the one holds if and only if the other holds, you have thereby shown them to be logically equivalent. So we have a syntactic way of sort of overcoming the deficiency that we saw in chapter 5 when it came to semantics. So let's go ahead then and prove it. Prove that A and B here are syntactically logically equivalent, and that means you have to show what? Well, by definition, it means you have to show it's a theorem that this, right, it's going to look like this. You have to show this if and only if, right, the other one, right? You have to show that this whole big thing here, this big sentence is in fact a theorem, because that's what the definition of syntactic logical equivalence requires. So you're going to be showing that this is in fact a theorem to prove that this sentence is logically equivalent to this sentence. So let's go ahead and do that now. So pause now and see if you can't show that this whole thing is in fact a theorem, thereby establishing that this sentence is logically equivalent to this sentence. Pause now. Okay, hopefully you were able to figure it out. And if you were to reverse engineer this or just look at it, one of the things that would occur to you is that this is a biconditional, and we have a technique for proving biconditionals harkening back to chapter 3. Okay, and it's the same technique here. And the technique is, okay, if I reverse engineer this, I use equiv, and I basically get two conditionals out of it. I get this conditional, which is the left to right direction, and I get this conditional, which is the right to left direction. So left to right, right to left. Taking those conditionals one at a time, right, is basically the strategy. So I assume the antecedent of the first one, I derive the consequent using com, and then I close out. I assume the antecedent of the first one, right, here, of the right to left direction, and then I get the consequent again by com, and then I get the right to left direction altogether here in 6. I conjoin them, right, using conjunction, and then I equiv back to the original. So I've proven not only that this is a theorem, but by definition I've proven that this sentence is logically equivalent to this sentence, because by definition they're syntactically logically equivalent if and only if they're sort of corresponding biconditional, which is what we have here, is in fact a theorem. And as we can see here, it is. So we have this really nice way of sort of overcoming the deficiencies of Chapter 5, whereas in Chapter 5 we could not show these two sentences, which are intuitively logically equivalent, to be so. We could not show them semantically logically equivalent. We can, using the techniques available to us here, show that the sentences are syntactically logically equivalent by demonstrating that this biconditional here is in fact a theorem of logic, which it is. Okay, let's investigate another important central syntactic concept, okay, and that's the concept of being logically inconsistent or syntactically logically inconsistent. So let's take a look at these two sentences just by example. So this one says everything is, let's say, red. Pick whatever you want out of Santa's bag. Whatever you picked out, it's guaranteed to be red. This says there exists at least one thing in Santa's bag that's not red. So intuitively, these are inconsistent. If this is true, this has to be false. And if this is true, this has to be false, right? So they have to take opposing truth values, right? They are inconsistent with one another, right? One sort of contradicts the other, as it were. So let's go ahead and formally define a pair of quantificational sentences like these two are syntactically logically inconsistent if and only if it's a theorem that the one, if and only if not the other. Okay? So, for example, if we're to show that this sentence, A here, is logically inconsistent with B, it would be tantamount to having to show it's a theorem, okay? It's a theorem that the first one, if and only if not the second one, okay? So it'd be tantamount to showing that this big thing here is in fact a theorem of logic. So let's go ahead and see if you can do that now. Go ahead and show that this sentence here is a theorem of logic, thereby establishing that this sentence, everything is F, and this sentence here, right there, something is not F, okay, are inconsistent with one another. Pause now. Okay, so hopefully you're able to figure it out. And again, reverse engineering is helpful. Assuming that you had this whole sentence available, one of the things you would do is you would equivocate and you would get two conditionals. And so what you do is you prove the left to right using conditional proof, and then you prove the right to left using conditional proof. You can join them together and voila. And that's exactly the routine that we've gone through here in order to prove that this is a theorem. And once again, that establishes by definition that this sentence and this sentence right here, this guy, are syntactically, logically inconsistent with one another. Okay, the one's truth, the one can be true if and only if the other is false. Would be a way of thinking about it semantically. Okay. And if you take higher level logic courses, you will establish formal relationships between semantics and syntax, right? So another really, really good example I should mention before we move on is that in Chapter 5, we could not show that a quantificational sentence was a tautology, right? And if you remember what a tautology is, it must be true, right? It couldn't possibly be false. So in order to show that a sentence was a tautology, you would have to show semantically, right, that it was true on every possible interpretation, and there's just too many possible interpretations. Well, you can show that a sentence is a tautology sort of in the syntactic sense by showing that it is a theorem, right? If you take more advanced courses in logic, you will see that only the syntactic theorems, okay, are the semantic tautologies and vice versa. And so there is that formal connection. That formal connection is beyond our scope here, but it's useful to sort of bear in mind that those higher level relationships between syntax and semantics hold, and that's what I'm trying to show you with syntactic logical equivalence and semantic logical equivalence. Okay, let's keep trucking along. Okay, what I want to do now is I want to explain a feature of the rule universal generalization, which we did not explain before, and which we are in a very good position to sort of understand now in the context of theorems. So let's recall the formal definition of universal generalization. let alpha be any universal pseudonym, gamma any individual variable, x, y, or z. Then given any sentence with a universal pseudonym in it, like u, one may infer the universally quantified sentence provided all of this, and the key feature for us right now is that alpha, the universal pseudonym, does not occur in any undischarged assumption. So the big question for us is, what does that mean, and why is that a necessary part of the rule of universal generalization? So I want to explain it in the context of an example. Okay, so the best way to explain, I think, what proviso A means and why it's necessary is to look at an example like this. So consider these two sentences just for a second, okay? So these two sentences are similar, but they are not the same, and they are by no means logically equivalent. So this one is a universally quantified sentence, okay? And this one is not a universally quantified sentence. It is a conditional, okay? And here's what I want to ask you, and you're just supposed to think about this intuitively for a second. Only one of these two sentences is a theorem of logic. Which of these two sentences is the theorem? Pause now. Okay, so the answer is that this one is a theorem and the other one is not a theorem. This is not a theorem of logic, okay? And this is going to manifest with respect to the condition A here. But just intuitively, to convince you that this is a theorem and that this is not a theorem, let's suppose that mx means x is a mammal, okay? So the first one here says, for any x you pick out of Santa's bag, if it's a mammal, then anything you pick out of Santa's bag is a mammal. Okay, and that's not true, right? I mean, it can be true, but it's not a theorem of logic. It's not guaranteed to be true, come what may. So imagine a world with 10 goldfish and a tiger, right? This says for anything you pick out, suppose you picked out the tiger, if it's a mammal, then anything you pick out is a mammal, but that's not true. There's those goldfish, right? Contrastively, this one says, if it's the case that everything is a mammal, then it's the case that everything is a mammal, which is undoubtedly true, right? So this one is the theorem and this one is not the theorem. Now, you might think that this one is a theorem and that you can prove it the following way. Let's take a look at okay, you might think, all right, Ash, look, this is a theorem, isn't it? I mean, look, I can prove it. Like, I picture this stripped down of any quantifiers, and that leaves me with if mu, then everything is m. So I've got, I make my assumption mu, and I'm looking for all y, my. Okay, it's just what reverse engineering would show you, everything you've been taught. And it's easy to get from this to this just by universally generalizing. So you close out, and you get this. And then you've got this, and boom, right? And so this is indeed a theorem of logic, and this is an incorrect. This is not a proof. Something has gone awry here. And again, just think about the goldfish counterexample. This can't be a theorem. It is not true, come what may. So something has to be wrong with this proof, and indeed there is. And what is wrong with it is that the assumption alpha occurs in an undischarged assumption, okay? So universal generalization says alpha is any pseudonym, okay? And if it occurs in an undischarged assumption, you cannot tack on the universal quantifier. And look, here's an assumption. It is not discharged, okay? This is an undischarged assumption. And so proviso A here prevents you from being able to universally generalize. This is an incorrect use of universal generalization, and that's why we have this proviso for universal generalization, and that's why that explains why although this might look like a theorem to you, it is in fact not, because it is an incorrect use of universal generalization. Contrastively, this is a theorem of logic, and you can prove it by assuming this and then deducing this, and I will leave that to you as an exercise. All right, logic fans, good work. Keep working on all those practice problems in the text to make sure you get this down. We'll consider theorems with relations and identity in separate sections of the text moving forward. Look forward to those videos, and we'll see you on the next one.